And I think it's important to kind of just talk about what antiderivatives are before we actually find them, right? So I talked about, before we even talked about antiderivatives, I talked about what a derivative did, right? Now, when we talked about derivatives, we started from my original function, which I called the OG function, or big F. We took a derivative, which brought us to, well, the first derivative, which usually is defined by either F or like F prime sometimes. The textbook uses little f for this, okay? Antiderivatives goes in the opposite direction. So when we're finding the antiderivative, we're starting at the first derivative, so we're given this. We want to go back and figure out what the original function is. So we're kind of going backwards, yeah.
So antiderivative is the original function of the derivative.
Yes. Mm-hmm.
Okay.
Yeah. Uh-huh. Oh, yeah, you're good. I didn't see you there. Here we go. And I just realized that my camera is pointing down here, and that's not fun. So let me just change this back so people on Zoom can see me. Okay. All right, so we're just going in the backwards direction now, which isn't too bad, but it is a little bit of work to kind of think about what the antiderivatives are. We did a lot of work before. We were able to figure out like the power rule of antiderivatives. So the backwards power rule. We did some like sine and cosine stuff. And we talked about a very particular power, 1 over x, right? So whenever we see 1 over x, we said that the derivative or the antiderivative was the natural log, but because the domains didn't match, we had to change the antiderivative to be the natural log of the absolute value of x, right? So that's what the opposite was. Another thing I didn't talk about yet in this class is when we find an antiderivative, there's actually multiple antiderivatives that work, right? If I add any constant to my function, I still get a function whose derivative is, well, the function that I have in the question. So to kind of combat that, we always add a plus c to our derivatives because any constant added to my function is also going to give me the same derivative. So whenever we find an antiderivative, make sure you add that plus c or plus some sort of constant value. Okay, we talked about the power rule, and then we started combining everything together in this chart here, right? So a couple rules, let's kind of just go over these real quick. The power rule is basically the same thing as the power rule, except of adding one, except for subtracting one, we're going to add one. And instead of multiplying, we're dividing, okay? We talked about natural log, e to the x is the same, b to the x is kind of the same, except for multiplying, we're dividing. We talked about cosine and sine. Let's kind of go through a couple more weird ones that I think are really important to notice to be able to figure out. There are more antiderivative rules to know, but I think these are the more important ones that you'll see throughout Calculus 2. What do you think the antiderivative of secant squared is? What function's derivative is secant squared? Yeah, tangent, right? The derivative of tangent is secant squared. So I know that the antiderivative of secant squared has to be tangent, okay? Now, what am I forgetting when I find an antiderivative? I always have to add c, good. So I always have to do a plus c, okay. Okay, can someone tell me a function whose derivative is secant tangent?
Secant x plus c.
Good, secant x plus c. I know, I feel like it's been a while since we've done derivatives, so now going backwards is a little bit harder. What's a function whose derivative is 1 over the square root of 1 minus x squared? Arc sine, good, or inverse sine. Yeah, this one, I feel like we haven't done this in a while, but it's the inverse sine plus c, right? Another way to say inverse sine is arc sine. And then there's one last one on the next page. Can someone give me a function whose derivative is 1 over 1 plus x squared? not cosine.
Tangent.
Or tangent, good. Good, so tangent inverse x plus c. These are I think the most important antiderivatives. You'll see a lot of these throughout Calc 2. There are more to know, but for now, let's just kind of learn these. All right. So let's kind of go through a few more examples. I do want to give you a chance to practice some of these on your own, but I think going through a few examples together might help us out here. This symbol, what is that symbol? Is it psi? Is it psi? Huh. I feel like a traitor. My family on my dad's side is Greek, and I don't know the Greek symbols. Yeah, I call it trident. All right, let's go through some of these. Now, if you don't like the Greek symbol, you can replace it with a different one. That's fine. And what I'm going to do is the same thing for derivatives. Whenever I see like a square root or a negative power, I'm just going to replace it with what the power actually means. What power is the square root really? What does the square root mean? Yeah, power of 1/2, right? So that kind of helps me out when I take derivatives or antiderivatives. Okay, so let's use our rules that are going backwards here. What's the antiderivative of 3 cosine psi? Take a look at your chart. Kind of hard to go backwards. Good. The antiderivative of cosine is sine, right? So going in our chart, I know that cosine goes to sine. So 3 cosine has to be 3 sine of, well, in this case, psi. All right. Next, we have to do the reverse power rule, right? We have something to the 1/2 power, which means we have to do the power rule. So let's kind of go through how we do this. We're multiplying by 3, so let's just keep the 3 on the outside. Whenever we do the reverse power rule, I'm going to take my variable psi. I'm going to take my power, and am I adding one or subtracting one? Adding, right? Because derivatives is subtracting, the opposite is adding, okay? And then I'm going to divide by the same thing that's in my power. So 1/2 plus 1, okay. Now, I've kind of went through and figured out what the antiderivative is. What did I forget to write? Plus C, perfect. All right, we're experts on plus C now. Now this looks a little messy, doesn't it? Let's kind of clean this up, make it a little bit nicer to look at. We have 3 sine of psi. We have a 3 as a multiple. What's 1/2 plus 1? 3/2, good. And then that would make the denominator also 3/2 plus c. Okay, I think we can clean this up a little bit more. Okay, whenever we have a denominator that's a fraction, I can change it to multiplication and flip over the fraction. So let me show you what that looks like. So we have the sine psi still staying the same. We still have the 3 up front, and instead of 3/2 on the bottom, it's going to be 2/3 up top, right? Okay, does everyone kind of see how I went from that step over to 2/3? Good. Now we're here. Well, looks like we're pretty lucky. The 3's cancel out, and we're left with, we're left with my face. Oh no.
What?
There we go. All right. We're left with 3 sine of psi plus 2 psi to the 3/2 plus c. And that is my final antiderivative. Okay. Any questions on example number 5? All right. Why don't we continue on? I want to do example 6 with you, and then maybe I'll try to leave you on your own. Yeah.
Is there nothing else we can know about the derivative? We can't solve for C. We can't.
We'll talk about cases where we can solve for C. When we're finding the general antiderivative, and we're not given any other information than what the derivative is, we can't do anything but just add c. But we'll talk about that a little bit
If we
later.
were to take the derivative of that, we would get the original.
Yeah, so a good way to check to see if your answer is right is just to take the derivative of your answer, right? So if you're ever confused to see if you got your answer right, you can always just take the derivative of what you got. And if you don't get what the question asked, then you know that you did something a little bit wrong. Okay. All right. Let's move on to example number 6 and see what we can do here. So same type of question, we want to find the general antiderivative of 3 sine plus 4x to the 8th power, which I think is a little bit easier than what we just did above. What's the antiderivative of 3 sine?
3 negative cosine.
Good, 3 times negative cosine of x, right? Because the antiderivative of sine is negative cosine. All right. The next one says 4x to the 8th. This is a power function. So I'm just going to keep the 4 over here. What's the antiderivative of x to the 8th power?
X to the 9 over 9.
Perfect. You add 1 to the power and you divide by that same new power. Okay, so that's kind of the reverse power rule. What I forget to write? Let's see. Perfect. All right. I'm just going to clean this up a little bit. It looks like we have -3 cosine of x plus 4/9 x to the 9th plus c. This is my antiderivative of my function. Now, this one's a little bit easier to do. So let's actually go through and check to see if we got the right answer. Okay. So I'm going to go ahead here and let's check to see if we got our answer right. Okay. Now, to check, we literally find the derivative of our answer. Okay. What's the derivative of -3 cosine?
-3 negative sine.
Good. -3 times negative sine. Okay. What's the derivative of 4/9 x to the 9th? Well, 4/9 stays on the outside. What's the derivative of x to the 9?
9x to the 8.
9x to the 8th. And then what's the derivative of any constant c? What's the derivative of like 2? 0. Perfect. So that would be my derivative. Cleaning this up, we have 3 sine of x plus, well, the 9's cancel out, 4x to the 8th. And checking to see, it looks like that is what my function was. So it looks like what I found here is a true antiderivative of my function. I was right. All right. If you flip to the back page, I have, let's see, example 7 and example 8. If you want to give the next ones a try after that, that's fine. But why don't you try 7 and 8 and we'll come back in a little. Got it. So this is your final answer. Now you did check, right? Oh, so you're in the process of checking. Yeah. Okay, well, it looks like you have 4x to the 8.
Also with the negative.
The negative times the negative is positive. All right. Looks like we have some good answers. I think this is a little bit tricky going backwards. I know we've been going forwards this whole time, and I feel like making you go backwards is a little bit tricky. I think some extra practice on this on Wednesday might help. So I think that's what my plan is for Wednesday. But for now, let's kind of go through these 2 ones here. So we want to find what the antiderivative of 3 over t minus 2 over t squared is. I got Jude wrote this one to write this one up, right? Do you want to take us through how you got your answer?
So the first part with 3 over t, it's recognized as the derivative of the natural log. So
Yeah. Did you write a negative on your paper? I'm sorry, I didn't check to look. I don't think it should be negative. I think it should be positive, right?
yeah,
Yeah, I think you just. Yeah, you're good. All right, continue on.
but After that, I go to the next one, which is t 2 over t squared and it inverse of it. That's that. I mean,
Yeah.
I,
Yeah, you went backwards, right? Or you could have used the reverse power rule for this. And then you added C, right? Now, one thing I want to talk about with this is the power rule works for everything except for when the power of t or x is -1, right? So whenever we have something over x to the first power or something over t to the first power, we're not using the power rule. We're just going to make it ln of the absolute value, right? So that's kind of the one exception to the power rule here. Okay. The rest of the power rule works the same here. Any questions on example number 7? All right, moving on to example number 8. This one looked a little bit weird at first because, well, there was a fraction and 1 plus a squared, which I think scared everyone. But it actually wasn't as hard as I made it out to be. Maddie, do you kind of want to take us through your steps here?
Yeah. So first we did the 3e to the a, which is just 3e to the a.
Yep.
And then I took out the 2 from the top of the fraction,
Mhm.
which is the prime, and then that gave me the
Perfect. Perfect. Yeah, so this one, it looks really crazy, but that really is just the rule for arctangent, right? So it's not like you have to do anything with the power rule or the chain rule or something like that. Whenever you see this 1 over 1 plus x squared, it's literally just inverse tan. Okay. Any question on example number 8? All right. Now, do you think you would benefit from more practice on Wednesday with antiderivatives? Yeah, I think I didn't give that much practice today. So how about our plan for Wednesdays? We'll do a little bit more practice with this. So we get a little bit more comfortable with finding antiderivatives. But for now, let's kind of keep chugging along. Okay. Let's do example number 4, which I know it says example number 8 in the last one, but we're doing example number 4 now. This one's not asking us to find the general antiderivative anymore. It's actually asking us to find the particular antiderivative. And you might be wondering what that means. And I think it might make a little bit more sense when we actually just try to do the question, okay? Now, our derivative in this case is 3x to the -2. We want to find what the original function is, which means we want to find the antiderivative. Okay, so I guess we have to use power rule here because it's x to the -2 power. We have a 3 up front here. Okay, what's the antiderivative of x to the -2? What would be the new power of x? Would I add or subtract? I'd add 1, right? So instead of doing the power rule, which tells us to subtract 1, I'm going to add 1 this time, okay? And we're going to put that all over -2 plus 1. And then I also have to put a plus c, right? Okay, cleaning this up, we have 3 times x to the, -1 over -1 plus c, okay? And what's another way to write 3x to the -1 over -1? What's a cleaner way for that? -3 over x, right? Because the negative can go anywhere, and x to the -1 puts it in the denominator. Okay, so my antiderivative is really big F of x equals -3 over x plus c. Okay, now in this question, I know I said that big F represents the antiderivative, but since the question said that my derivative is f prime, my original function is really just little f. Does that kind of make sense? So to go from my original function to f prime, I know that the original function is little f. Okay, now this question tells me I want to find not the general antiderivative, which is what this is. This is the general antiderivative. But it wants me to find the particular antiderivative. And what that means is it doesn't want me to add c, it wants me to actually find what number c is, okay? And if I'm given an antiderivative, I can't really figure that out unless I have some extra information. The extra information is that f of 1 equals 2. How do you think I can find what C is if I know f of 1 equals 2?
So one equal percent x equal to 1, that's the equation equal to 2.
Okay, good. So we know that f of 1 is 2. I know that 1 is an x value and 2 is a y value of my original function, right? So what I can do is I can literally just plug in 2 for y, and I can plug in 1 for x, right? So 2 equals -3 over 1 plus c. Does everyone kind of see how I did that? Good. Okay, so here I just plug in x equals 1 and y equals 2. Okay, once I do that, let's clean this up. We have 2 equal to -3 plus c. To get c by itself, I can add 3 on both sides. So I know that c equals 5. Okay, so I literally just plugged in my function or my values. I got that c equals 5. What do you think my particular antiderivative is? F of x equals, yeah, -3 over x plus 5. This is my particular antiderivative. Oh my gosh, particular antiderivative. Okay, so we went from the general antiderivative to the particular antiderivative. We can find what c is as long as we have some more information about what the original function is. Okay, so it's literally kind of just a two-step problem here. All right, what do I want to do here? Did I have another one? Why don't you give example 9 a try? Okay, I don't think we're gonna have enough time to go over this whole thing fully because it is picture day. One thing I want to say just for next class, so I have this on my paper. If you take a look at example number 10, this should not say b prime of 1 equals 0. This should say b of 1 equals 0, okay?